Far out in the depths of our galaxy, approximately 15,000 light-years from Earth, something is pulsing. Every 44 minutes and 12 seconds, a beam of energy sweeps across the cosmos. Radio waves and X-rays flash together, perfectly in time, lasting just 2 minutes before fading back into silence. Then the cycle begins again. This is ASKAP J1832-0911. It was discovered in late 2023, and almost immediately astronomers knew they had found something they could not explain. Not a pulsar, not a magnetar, not a white dwarf, not a black hole. At least not in any form we've seen before. Its rhythm is too slow, its brightness is too high, and the fact that it emits both radio waves and X-rays at exactly the same moment has never been observed in any other object like this. To understand why this discovery matters, we must first understand what astronomers expected to find when they turned their instruments toward the sky that day, and what they did not expect, because ASKAP J1832-0911 does not fit into any category we have. It sits outside the boundaries of our models, and that is what makes it so compelling. Let us begin with the simplest question. What is this object? We do not know. That is the honest answer. But we can describe what it does. We can measure its behavior. We can count the seconds between its pulses. We can study the light it emits. And from those measurements, we can begin to ask better questions. ASKAP J1832-0911 lies in the constellation Scutum, embedded within the plane of the Milky Way. It is not in a distant galaxy. It is not beyond our reach. It is here, within our own spiral of stars, hidden among the gas and dust of the galactic disk. 15,000 light-years is not particularly far by cosmic standards. Many stars we observe are farther away. Yet this object remained invisible to us until very recently. Not because it was dim, but because no one was looking in the right way. The discovery required a combination of two things: a powerful radio telescope scanning the sky at the right moment, and an X-ray observatory entirely by chance pointing at the same patch of sky at the same time. Without both, we might never have known what this object truly was. The radio telescope was ASKAP, the Australian Square Kilometre Array Pathfinder, a grid of 36 dish antennas spread across the remote landscape of Western Australia, designed to survey the sky quickly and efficiently. ASKAP is built to find transients, objects that change, objects that flash or pulse or appear suddenly where nothing was visible before. In late 2023, during one of its routine scans, ASKAP detected something unusual. A single point in the sky producing an extraordinarily bright burst of radio waves. Not a faint whisper, not a marginal signal buried in noise, but a powerful, coherent pulse of energy, measured at 10 to 20 Janskys. For context, most radio pulsars emit far less than this. A Jansky is a unit of radio brightness. 20 Janskys is blindingly bright by radio astronomy standards, and the pulse lasted for about 2 minutes. Then it stopped. 44 minutes later, it happened again. Same location, same brightness, same duration. The pattern repeated, cycle after cycle, like a cosmic metronome. At first, the team thought it might be a known type of object, perhaps a pulsar they had not catalogued yet, perhaps a flare star, perhaps some kind of interference. But as they studied the signal more carefully, they realized it did not match anything in the archives. Pulsars spin. Neutron stars, collapsed remnants of massive stars, rotate at incredible speeds. They emit beams of radio waves from their magnetic poles, and as they spin, those beams sweep past Earth like a lighthouse. Most pulsars pulse every few seconds. Some pulse every few milliseconds. The fastest known pulsars spin hundreds of times per second. But 44 minutes? No pulsar spins that slowly. If this were a neutron, star rotating once every 44 minutes, it would be spinning thousands of times slower than any pulsar ever discovered. And at that speed, according to everything we understand about neutron stars, it should not be emitting radio waves at all. The mechanism that powers pulsar radio emission depends on rapid rotation, on strong magnetic fields threading through a spinning star, on charged particles accelerated to near light speed in the magnetosphere. Slow down the spin too much and the mechanism shuts off. The pulsar dies. It becomes invisible. This is called the death line. Below a certain rotation speed, pulsars simply stop pulsing. ASKAP J1832-0911 is far below that line, and yet it pulses. So the object was strange, interesting, worth investigating further. But then the team made a second discovery, one that changed everything. They searched through archival data from other telescopes, looking for anything that might have observed the same region of sky around the same time, and they found something extraordinary. NASA's Chandra X-ray Observatory had been pointing at that exact patch of sky during the same observing window, not because anyone planned it, not because Chandra was tracking this object, but purely by coincidence. Chandra is an X-ray telescope. It orbits Earth, studying the high-energy universe. X-rays from hot gas, X-rays from black holes, X-rays from exploding stars. Its field of view is small, much smaller than ASKAP's Wide Radio Survey. The chance of both telescopes observing the same object at the same time was vanishingly tiny. But it happened. And when the team examined Chandra's data, they saw X-ray flares. Bursts of high-energy light, each lasting about 2 minutes, repeating every 44 minutes. The same rhythm, the same timing, perfectly aligned with the radio pulses, radio and X-rays, together. This had never been seen in an object like this before. Let us pause for a moment and consider what this means. Radio waves and X-rays are very different kinds of light. They sit at opposite ends of the electromagnetic spectrum. Radio waves are low energy, long wavelength. They pass through dust and gas with ease. They are produced by different physical processes than X-rays. X-rays are high energy, short wavelength. They are absorbed by matter. They are typically produced by extremely hot gas or by particles accelerated to enormous speeds. For both to flash at exactly the same moment suggests they are coming from the same source, the same event, the same physical mechanism. Whatever is happening at ASKAP J1832-0911, it is generating both radio waves and X-rays in perfect synchronization, every 44 minutes. Like clockwork. This is not how pulsars behave. Most pulsars emit only in radio. Some emit in visible light or gamma rays as well. A few emit X-rays, usually faint, steady X-rays from their hot surfaces. But coordinated, simultaneous pulses of radio and X-rays, repeating on a 44-minute cycle, had never been observed. The team published their findings in the journal Nature in early 2025. The paper was titled Detection of X-ray Emission from a Bright Long-Period Radio Transient. The discovery made headlines, not because it was flashy, not because it was loud or dramatic, but because it was genuinely puzzling. Andy Wang, the lead author, described finding the X-ray signal as like finding a needle in a haystack. The odds of Chandra and ASKAP both observing the same rare transient at the same time were extraordinarily low. and yet it happened. And now astronomers had to make sense of it. Before we explore the possible explanations, we need to understand the broader context. ASKAP J1832-0911 belongs to a newly recognized class of objects called long-period radio transients, or LPTs. These are sources that emit radio pulses separated by minutes or hours, rather than seconds or milliseconds. The first LPT was discovered in 2022. Since then, about 10 have been found. They are rare, or perhaps they are common but difficult to detect. Most radio surveys are designed to find fast transients, pulsars, fast radio bursts, signals that flash and disappear in fractions of a second. Long-period transients are harder to catch. You need a telescope that can survey large areas of the sky continuously, watching for slow, periodic signals that might appear anywhere. ASKAP is ideal for this. Its wide field of view and advanced processing allow it to monitor many square degrees at once, looking for objects that pulse slowly. But even among LPTs, ASKAP J1832-0911 is unique. Until this discovery, no LPT had ever been seen emitting X-rays. They were radio-only objects, their nature unknown, their origins debated. Some astronomers thought they might be unusual pulsars. Others suggested they could be white dwarfs with strong magnetic fields. Others proposed more exotic ideas. But without X-ray detections, there was no way to confirm any model. ASKAP J1832-0911 changed that. The X-rays provided a critical clue. They told us that whatever this object is, it is not just a radio emitter. It is energetic enough to produce high-energy radiation as well. And that narrows the possibilities. Not by much, but enough to guide the next steps. So what could it be? Let us consider the options, one by one, slowly and carefully. The first possibility is that it is a neutron star, but not an ordinary one. Neutron stars are the collapsed cores of massive stars. When a star more than 8 times the mass of the Sun exhausts its fuel, it explodes in a supernova. The outer layers are blown away. The core collapses under its own gravity, compressing protons and electrons together into neutrons. What remains is a sphere about 20 kilometers across, containing more mass than the Sun. The density is almost incomprehensible. A teaspoon of neutron star material would weigh 1 billion tons on Earth. Neutron stars spin rapidly. They have powerful magnetic fields, millions or billions of times stronger than Earth's. As they spin, their magnetic fields drag charged particles around, accelerating them to near light speed. Those particles emit radiation, often in narrow beams from the magnetic poles. If one of those beams sweeps across Earth, we see a pulse. That is a pulsar. Most pulsars spin once every few seconds or faster. Some spin hundreds of times per second. These are called millisecond pulsars. But all pulsars slow down over time. Their rotation gradually loses energy to magnetic braking and radiation. They spin slower and slower until eventually they cross the death line and stop pulsing. The slowest known pulsars have periods of a few seconds, maybe 10 seconds at most, not 44 minutes. So if ASKAP J1832-0911 is a neutron star, it must be something unusual. One idea is that it is a magnetar. Magnetars are a special kind of neutron star with extremely strong magnetic fields. Fields 1,000 times stronger than typical pulsars. Strong, enough to distort the structure of atoms. Strong enough to power enormous bursts of X-rays and gamma rays. Young magnetars spin rapidly like ordinary pulsars, but as they age, they slow down. Their magnetic fields decay. They become quieter. Could ASKAP J1832-0911 be an old magnetar, one that has spun down to an extraordinarily slow rotation period? Some researchers have suggested this. They propose that if a magnetar is old enough, perhaps 500,000 years or more, it could theoretically rotate once every 44 minutes. And if it still has a strong magnetic field locked in its crust, it might still produce periodic bursts of energy. But there are problems with this idea. First, no magnetar has ever been observed spinning this slowly. The slowest known magnetar has a period of around 12 seconds. 44 minutes is more than 200 times slower. Second, magnetar radio emission is poorly understood. Most magnetars do not emit radio waves at all. A few have been observed to emit brief radio bursts during outbursts, but sustained, regular radio pulses from a magnetar are not something we have seen. And third, the brightness of ASKAP J1832-0911 is hard to explain. It emits extremely powerful radio pulses, far brighter than most pulsars. If this is a magnetar, it is unlike any other. The researchers who proposed this model acknowledged the difficulties. One study noted that if ASKAP J1832-0911 is an old magnetar, explaining the radio emission challenges existing models. In other words, this hypothesis stretches magnetar theory to its limits. It is not impossible, but it requires assuming things we have not seen before. So let us consider a second possibility. Perhaps it is not a neutron star at all. Perhaps it is a white dwarf. White dwarfs are the remnants of lower mass stars, stars like the Sun. When such a star exhausts its fuel, it gently sheds its outer layers, leaving behind a dense core about the size of Earth. White dwarfs are much less dense than neutron stars. They are not as extreme, but they can still have strong magnetic fields. Some white dwarfs are highly magnetized, and if a white dwarf has a companion star, matter can flow from the companion onto the white dwarf, releasing energy. A few objects have been discovered in recent years that might be white dwarfs emitting periodic radio pulses. These systems involve a white dwarf in a binary with a complex magnetic field that generates radio emission. Could ASKAP J1832-0911 be something like this? A magnetized white dwarf in a closed binary system? The 44-minute period could in principle be explained by the orbital period of the binary, or by the rotation of the white dwarf itself. And if matter is accreting onto the white dwarf, that could explain the X-rays. Accretion releases gravitational energy, heating the infalling gas to millions of degrees, producing X-rays. This model has some appeal. White dwarf binaries are known to exist. Some are powerful X-ray sources, and recent discoveries have shown that white dwarfs can emit radio waves under certain conditions. But again, there are problems. The radio brightness of ASKAP J1832-0911 is far higher than any known white dwarf system. Most white dwarf pulsars are faint in radio. This object is extraordinarily bright, and generating the observed X-ray luminosity requires a specific type of accretion. The details are complicated, but essentially the white dwarf would need to have an extreme magnetic field comparable to those found in neutron stars. Such fields are theoretically possible in white dwarfs, but they are rare, and pairing such a field with the right kind of binary companion at the right distance, accreting at the right rate, is a lot to ask. Some researchers have suggested this scenario remains plausible, but it is speculative. The data do not yet confirm or rule it out. So we have two main candidates: a neutron star spinning impossibly slowly, or a white dwarf binary with an unusually strong magnetic field. Both require us to stretch existing models. Both require special circumstances. But there is a third possibility, one that is even more radical. Perhaps ASKAP J1832-0911 is not a star at all. Perhaps it is a black hole, not a stellar mass black hole. Those are typically quiet in the radio and X-ray bands unless they are actively accreting matter. But an intermediate mass black hole. Intermediate mass black holes, or IMBHs, are black holes with masses between 100 and 100,000 times the mass of the Sun. They are heavier than stellar black holes, but lighter than the supermassive black holes found at the centers of galaxies. IMBHs are mysterious. We are not sure how many exist. We are not sure how they form. Only a handful have been tentatively identified, but if they exist, they could power jets. Beams of particles and radiation launched from near the black hole's event horizon, accelerated by the black hole's spin and magnetic field. A team led by Nathaniel in 2025 proposed that ASKAP J1832-0911 could be an intermediate mass black hole with a precessing accretion disk. Precession means the disk wobbles, like a spinning top that tilts and wobbles as it slows down. If the inner part of the accretion disk is tilted relative to the black hole's spin, a phenomenon called lens-thirring precession can occur. The disk wobbles around the black hole's spin axis, dragging the jet with it. As the jet precesses, it sweeps across our line of sight once per precession period. If the precession period is 44 minutes and the jet emits both radio waves and X-rays, this could explain what we see. The model is elegant. It simultaneously explains the periodicity, the brightness, and the dual radio and X-ray emission, but it requires an intermediate mass black hole in our galaxy with an accretion disk, precessing at exactly the right rate. This is not impossible, but it is rare. And finding one by chance in a survey like ASKAP would be extraordinarily lucky. Or perhaps not lucky. Perhaps there are many such objects and we have simply not noticed them before. The black hole hypothesis is radical, but it is not dismissed. Some researchers consider it a viable explanation. Distinguishing between these models will require more data. Higher resolution observations, better timing measurements, detailed studies of the polarization of the radio emission. For now, all three possibilities remain on the table. An ultra-slow magnetar, a magnetized white dwarf binary, an intermediate mass black hole, or perhaps something else entirely, something we have not thought of yet. Because that is the fourth possibility, that ASKAP J1832-0911 represents a new class of object, a new phenomenon, something that does not fit into our existing categories because it operates by a mechanism we have not yet discovered. This is not science fiction. It is simply an acknowledgement that the universe is larger and more complex than our models. We have only been studying the sky with radio and X-ray telescopes for a few decades. Every year, we find new types of objects, new behaviors, new surprises. ASKAP J1832-0911 may be one of those surprises, a hint that our theories are incomplete, an invitation to expand our understanding. Let us return to the observations themselves, to what we can measure and what we can see. The pulse itself lasts about 2 minutes. Out of a 44-minute cycle, the object is active for roughly 2 minutes, then silent for 42. This is called the duty cycle, the fraction of time the source is emitting. For ASKAP J1832-0911, the duty cycle is about 5%. Most of the time it is dark. During those 2 minutes, the radio and X-ray emissions rise together, peak together, and fade together. the light curves match almost perfectly. This tells us something important. It tells us that the radio and X-ray emissions are coupled. They are not independent processes, happening at the same location by coincidence. They are linked, driven by the same event, perhaps the same region of a magnetosphere, perhaps the same jet, perhaps the same burst of particles crashing into surrounding material. The radio emission is highly polarized. Polarization means the radio waves vibrate in a preferred direction rather than randomly. This is a sign of a strong magnetic field. Only a powerful, ordered magnetic field can produce highly polarized radio waves. So whatever this object is, it has a strong magnetic field. That is consistent with a neutron star or a magnetar. It is also consistent with a highly magnetized white dwarf. It is even consistent with a black hole surrounded by magnetized plasma. Polarization alone does not tell us which model is correct, but it does constrain the possibilities. The X-ray luminosity is modest, about 10 to the 33 ergs per second. For comparison, the Sun's total luminosity is about 10 to the 33 ergs per second as so the X-ray output of ASKAP J1832-0911 is roughly comparable to the Sun's total energy output. That is not enormous by astrophysical standards, but it is significant. The radio luminosity is harder to calculate because radio brightness depends on the emitting mechanism and the bandwidth. But the observed flux is very high. This is one of the brightest radio transients known. The combination of bright radio emission and modest X-ray emission is unusual. Most X-ray sources that emit radio waves are much fainter in radio, and most bright radio sources do not emit X-rays. ASKAP J1832-0911 sits in a strange middle ground. There is another detail worth noting. The object's brightness has changed over time. Follow-up observations conducted months after the initial discovery showed that both the radio and X-ray emissions had faded dramatically, by more than an order of magnitude, perhaps even more. This suggests that ASKAP J1832-0911 is variable on long time scales. It is not a steady, unchanging source. It flares, it dims, it changes. Archival data hint that it may have turned on relatively recently. One report suggests it became about 10,000 times brighter than typical faint radio sources in early 2024. This variability adds another layer of mystery. What causes the long-term changes? Is the object evolving? Is it accreting more or less matter over time? Is its magnetic field reconfiguring? We do not know. But the variability suggests that whatever powers ASKAP J1832-0911 is not a fixed, stable process. It is dynamic. It changes. And that might be another clue. Let us consider the location again. 15,000 light-years away, in the plane of the Milky Way. The galactic plane is crowded, filled with stars, gas, dust. It is difficult to observe at visible wavelengths because dust blocks the light. But radio waves pass through dust, so do X-rays to some extent. This is why ASKAP and Chandra could see the object. It is invisible in visible light, hidden behind layers of interstellar material. But in radio and X-rays, it shines through. There is no obvious companion star, no visible counterpart. Infrared surveys have been checked and nothing conclusive has been found. This does not rule out a binary system. The companion could be faint, it could be obscured by dust, or it could be something that does not emit much light, like a low-mass star or a brown dwarf. But the lack of a visible companion makes it harder to confirm the binary models. If ASKAP J1832-0911 were a white dwarf binary, we might expect to see the companion star, or at least some sign of an accretion disk. The absence of such signatures is not definitive, but it is worth noting. So where does this leave us? We have an object pulsing every 44 minutes, emitting bright radio waves and modest X-rays, perfectly in sync, located in the Milky Way, about 15,000 light-years from Earth. Its rotational oscillation period is far too slow for any known pulsar. Its emission properties do not match any known magnetar. Its brightness is too high for most white dwarf models. And while a black hole hypothesis is intriguing, it requires assumptions we cannot yet verify. The object has been observed extensively since its discovery. Multiple radio telescopes have tracked it. Meerkat in South Africa, the Very Large Array in New Mexico, the Giant Meter Wave Radio Telescope in India, the Australia Telescope Compact Array. Each observation adds more detail, more constraints, more pieces of the puzzle. X-ray observatories continue to monitor it. Chandra has observed it again. The European Space Agency's Einstein probe has looked at it. XMM Newton and NASA's Swift are on the target list. But even with all this data, the fundamental question remains unanswered. What is ASKAP J1832-0911? Perhaps the answer will come from more observations. Perhaps the next detection will reveal something new. A subtle change in the pulse shape, a drift in the period, a new emission feature. Or perhaps the answer will come from theory, from someone finding a way to extend existing models just enough to accommodate this object. Or perhaps the answer will come from finding more objects like this. If ASKAP J1832-0911 is not unique, if there are others pulsing slowly across the galaxy, we can begin to study them as a population, to look for patterns, to understand what they have in common. Already astronomers are searching for X-ray counterparts to the other known long-period transients. Are any of them also emitting X-rays? Or is this object special? The next generation of telescopes will help. The square-kilometre array, when complete, will be the most sensitive radio telescope ever built. It will find faint, slow-pulsing sources that current instruments cannot detect. Proposed X-ray missions, like the Advanced X-ray Imaging Satellite, will be able to survey larger areas of the sky in X-rays, making it easier to catch rare transients by chance. Within a decade, we may have dozens or even hundreds of similar objects to study, and then perhaps the mystery will begin to unravel. For now, ASKAP J1832-0911 stands alone. A single example, a cosmic puzzle with no clear solution. But let us step back for a moment. Let us consider what it means to discover something we cannot explain. In astronomy, this happens more often than you might think. We point our telescopes at the sky, and the universe shows us things we did not anticipate, things that do not fit our models, things that challenge our assumptions. Pulsars themselves were once a mystery. When they were first discovered in 1967, no one knew what they were. The regular radio pulses were so precise, so mechanical, that some astronomers half seriously wondered if they might be signals from an alien civilization. They were even briefly called LGM signals, little green men. Of course, they were not aliens, they were neutron stars, spinning lighthouse beacons of natural origin. But it took time to reach that understanding. Years of observation, theoretical work, careful analysis. ASKAP J1832-0911 may follow a similar path. What seems inexplicable now may become clear in time, or it may remain mysterious for longer. Some cosmic puzzles take decades to solve. The important thing is that we keep looking, keep measuring, keep thinking, because every mystery solved reveals new questions, every answer opens new doors, and ASKAP J1832-0911 has already opened several doors. One of those doors leads to a fundamental question about stellar remnants. When massive stars die, they leave behind neutron stars or black holes. When lower mass stars die, they leave behind white dwarfs. These remnants are not inert. They are not dead in the way a rock is dead. They are dynamic objects shaped by gravity, magnetism, rotation. And we thought we understood the rules governing how they behave. We thought we knew how fast they could spin, how slowly they could spin, what kinds of radiation they could emit. ASKAP J1832-0911 suggests those rules may be incomplete. Perhaps neutron stars can spin far slower than we thought and still emit radiation. Perhaps there is a mechanism we have not considered. Perhaps white dwarfs can have stronger magnetic fields than we realized. Perhaps they can power radio emission in ways we did not predict. Or perhaps there is something in between, a type of object that does not fit neatly into our categories. The universe does not care about our categories. It does not organize itself according to our textbooks. It simply is. And it is our task to observe, to measure, and to understand. Another door leads to the question of how common these objects are. ASKAP J1832-0911 was found by chance, or rather by a combination of chance and capability. ASKAP's wide field of view made it possible to detect the radio pulses. Chandra's presence in the same patch of sky made it possible to detect the X-rays. Without both, we would not know what this object truly is. How many similar objects exist but have not yet been found? How many are pulsing slowly, hidden in the galaxy, waiting to be discovered? If ASKAP J1832-0911 is rare, that tells us something. It tells us that whatever produces it requires special conditions, a rare combination of circumstances. But if it is common, if there are many such objects scattered throughout the Milky Way, that tells us something else. It tells us that this is a natural stage in the life of certain stars, a phase we simply had not noticed before. The answer matters because it shapes how we understand stellar evolution, how stars live, how they die, what they leave behind. Some astronomers believe we are on the verge of finding many more. They point to the fact that ASKAP has only been fully operational for a few years, that long-period transients were only recognized as a class in 2022. We have barely begun to survey the sky systematically for slow pulsing sources. As our instruments improve, as our surveys become more sensitive, we will find more. And with each new discovery, the picture will become clearer. Or perhaps more complicated. That happens too. Let us think about the 44-minute period itself. This number is central to the mystery. 44 minutes and 12 seconds to be precise, remarkably regular, remarkably stable. What sets this timescale? In astrophysics, there are several natural clocks, several processes that can produce regular periodicities. The most common is rotation. A spinning star or stellar remnant pulses as it rotates, with the pulse period equal to the rotation period. But as we have discussed, no known neutron star rotates this slowly. And white dwarfs can rotate at any speed, but rotation alone does not explain the emission mechanism. Another natural clock is orbital motion. In a binary system, two objects orbit each other with a characteristic period. 44 minutes could in principle be an orbital period. Two objects, very close together, orbiting once every 44 minutes. But this raises questions. What kinds of objects? How close? And how does the orbit produce the observed emission? Some models propose that the emission is tied to interactions between the two objects. Perhaps mass transfer, perhaps magnetic interactions. But the details are complex and the models are not yet fully developed. A third natural clock is precession. We mentioned this earlier in the context of the black hole model. Precession is a wobbling motion, like a spinning top whose axis traces a circle as it wobbles. Accretion disks can precess, magnetic fields can precess. Even the rotation axis of a neutron star can precess if the star is not perfectly symmetric. Precession timescales can be long, minutes, hours, even days, depending on the system. So a 44-minute precession period is plausible, at least in principle. But again, this requires specific conditions. A tilted disk, a strong magnetic field, a source of energy to sustain the emission. There is a fourth possibility, less commonly discussed, that the periodicity is not directly tied to any physical motion. Perhaps it is an oscillation, a natural frequency of the system, like a bell ringing at its resonant frequency. Certain kinds of instabilities in accretion disks can produce periodic oscillations. Certain configurations of magnetic fields can oscillate. This is more speculative, but it is not impossible. The truth is, we do not know what sets the 44-minute clock. We can list possibilities. We can build models. But we cannot yet say with certainty which one is correct. And that uncertainty is part of what makes ASKAP J1832-0911 so compelling. It is a clock ticking in the darkness, and we do not yet know what mechanism is counting the seconds. Let us turn our attention now to the emissions themselves. The radio waves and X-rays. Why do they appear together? Why are they synchronized? This is not a trivial question. Radio emission and X-ray emission are usually produced by different processes. Radio waves, especially coherent radio waves like those from pulsars, are produced by electrons moving through magnetic fields. The electrons spiral along magnetic field lines, accelerating, and that acceleration produces radiation. In pulsars, the radio emission comes from the magnetosphere, the region around the neutron star where the magnetic field controls the motion of charged particles. The exact mechanism is still debated, but the key point is that coherent radio emission requires specific conditions. Strong magnetic fields, relativistic particles, organized motion. X-rays, on the other hand, are typically produced by very hot gas, temperatures of millions of degrees, or they can be produced by synchrotron radiation, electrons spiraling in magnetic fields at extreme energies, emitting high-energy photons. Or they can be produced by accretion, matter falling onto a compact object, releasing gravitational energy as heat and radiation. Each of these mechanisms is well understood individually, but having them operate together in perfect synchronization is unusual. What does it tell us? It tells us that the radio and X-ray emissions are not independent. They are coupled, linked by a common driver. Perhaps they come from the same region, the same volume of space. If the object has a magnetosphere, perhaps both the radio and X-ray emissions originate there. Electrons accelerated in the magnetosphere could produce coherent radio waves, and at the same time some of those electrons could emit X-rays through synchrotron radiation. This would explain the synchronization. The same burst of particles produces both signals. Alternatively, if the object has a jet, the radio and X-rays could both come from the jet. Jets are known to emit across a wide range of wavelengths. A sudden increase in jet power could produce both radio and X-ray flares simultaneously. Or perhaps the emissions come from different regions, but they are triggered by the same event. Imagine a magnetic field line snapping and reconnecting. This releases energy suddenly. Some of that energy goes into accelerating particles that produce radio waves. Some goes into heating gas that emits X-rays. The two emissions are not from the same place, but they are both consequences of the same magnetic event. Any of these scenarios could be correct, or none of them. We do not yet have the data to distinguish between them. What we do know is that the synchronization is precise. The radio and X-ray light curves match closely. They rise together. They peak together. They fade together. This precision is itself a clue. It suggests that whatever mechanism links them operates on short timescales, seconds or less. If there were a significant delay between the radio and X-ray emissions, we would see it in the data. The peaks would be offset, the light curves would not align, but they do align, which means the coupling is tight, immediate. This will be important for testing models. Any proposed explanation must account for the synchronization. It is not enough to explain the radio emission and the X-ray emissions separately. The model must explain why they happen together. Let us consider the energy budget. How much energy does ASKAP J1832-0911 release with each pulse? The radio luminosity is difficult to calculate precisely without knowing the emission mechanism, but a rough estimate based on the observed flux and distance suggests each radio pulse releases on the order of 10 to the 35 ergs. The X-ray luminosity integrated over the 2-minute pulse is about 10 to the 36 ergs, so the total energy per pulse is roughly 10 to the 36 ergs, maybe a bit more, depending on emissions at other wavelengths we have not measured. For comparison, the Sun emits about 10 to the 33 ergs per second, so in 2 minutes the Sun emits about 10 to the 35 ergs. ASKAP J1832-0911, during its 2-minute pulse, emits about 10 times more energy than the Sun does in the same time. That is not an enormous amount by astrophysical standards. Many pulsars emit more. Magnetars can emit far more during outbursts, but remember, ASKAP J1832-0911 is pulsing very slowly. Most of the time it is not emitting at all. If we average the energy output over the full 44-minute cycle, the mean luminosity is much lower, about 10 to the 34 ergs per second. This is modest, comparable to a typical pulsar perhaps, but the fact that all that energy is released in brief bursts is interesting. It suggests the energy is stored somehow, then released periodically, like a dam holding back water, then opening its gates for 2 minutes every 44 minutes. What stores the energy, and what triggers the release? In a neutron star or magnetar, energy can be stored in the magnetic field. The field threads through the star and the surrounding space. If the field lines twist or shear, energy builds up. When the field relaxes or reconnects, energy is released suddenly. This is thought to be the mechanism behind magnetar outbursts. Could something similar be happening in ASKAP J1832-0911? Could the magnetic field be building up energy for 42 minutes, then releasing it in a 2-minute burst? It is possible. But why would this process be so regular? Why exactly 44 minutes, cycle after cycle? In a white dwarf binary, energy can be stored in an accretion disk. Matter spirals inward, building up until some instability triggers a sudden release. But again, why so regular? In a black hole system, energy could be stored in the accretion flow. The precessing jet model suggests that the jet is always emitting, but we only see it when it points toward us, once per precession cycle. In that case, the energy is not being stored and released, it is being beamed. We see the pulse not because the source turns on, but because the beam sweeps across our line of sight. This is similar to how a lighthouse works. The light is always on, but you only see it when the beam points towards you. If ASKAP J1832-0911 is a lighthouse, then the 44-minute period is simply the time it takes for the beam to sweep around and point at us again. This interpretation changes how we think about the energy budget. We are not seeing the total energy output. We are seeing only the fraction that happens to be beamed toward Earth. The true luminosity could be much higher, or it could be the same if the beam is very broad. Without knowing the beaming geometry, we cannot say for certain. These are the kinds of details that matter. They seem small, but they shape our understanding of what is happening. Let us consider the polarization again. This is an important observational constraint. Radio waves from ASKAP J1832-0911 are highly polarized. This means the electric field of the radio waves oscillates in a preferred direction. Polarization is a signature of ordered magnetic fields. Random magnetic fields produce unpolarized radiation. But if the magnetic field has a coherent structure, the emitted radio waves will be polarized. The degree of polarization tells us about the field geometry. The way the polarization changes with time or frequency can tell us even more. For pulsars, polarization is a powerful diagnostic tool. By measuring how the polarization angle sweeps across a pulse, astronomers can map the magnetic field geometry near the neutron star. For ASKAP J1832-0911, detailed polarization measurements are still being analyzed, but the fact that the emission is highly polarized is consistent with a magnetized compact object. A neutron star with a dipole magnetic field would produce polarized radio emission. So would a white dwarf with a strong field. Even a magnetized accretion disk around a black hole could produce polarized emission depending on the field structure. So polarization does not by itself tell us which model is correct, but it does rule out certain scenarios. For example, if the emission were coming from hot chaotic gas with tangled magnetic fields, we would not expect high polarization. The fact that we see it suggests the emission region is ordered, not chaotic. This is consistent with a pulsar-like mechanism, or a jet, or a magnetosphere. It is less consistent with, say, a thermal X-ray source surrounded by unmagnetized gas. So the polarization is another piece of the puzzle, another constraint that any successful model must satisfy. There is also the question of variability, the long-term changes in brightness. When ASKAP J1832-0911 was first detected, it was extremely bright, both in radio and in X-rays. But months later, follow-up observations showed it had faded, significantly, by more than an order of magnitude. The pulses were still there, still regular, still every 44 minutes, but fainter. What does this mean? It could mean the object is evolving. Perhaps it was in an active state when it was discovered, and it has since settled into a quieter state. Many astrophysical objects show this kind of behavior. Magnetars, for example, have outbursts. They flare up, becoming much brighter for weeks or months, then fade back to a quiescent state. Accreting systems can also change brightness. If the accretion rate increases, the system becomes brighter. If the accretion rate drops, it fades. So the suggests that whatever powers ASKAP J1832-0911 is not constant. It fluctuates, it changes. This adds another layer of complexity. Not only must we explain the 44-minute pulses, we must also explain why the overall brightness changes on timescales of months. Perhaps the two are related. Perhaps the mechanism that produces the pulses also controls the long-term brightness. Or perhaps they are independent. Perhaps the pulses are a fixed feature, like the ticking of a clock, but the brightness is controlled by something else, like the flow of fuel into the engine. We do not know. But the variability is important. It tells us this is not a static system. It is dynamic. And dynamic systems are often easier to understand because we can watch them change, we can see cause and effect. If we can catch ASKAP J1832-0911 during a bright state and a faint state, we can compare. We can look for differences. And those differences might tell us what is changing and why. Archival data suggests the object may have turned on relatively recently, perhaps in early 2024. Before that, it may have been much fainter or even undetectable. This raises an interesting possibility. Perhaps ASKAP J1832-0911 has not always been pulsing. Perhaps something triggered it, some event, some change in its environment or its internal structure. What could trigger such a change? In a binary system, a change in the orbital separation or the accretion rate could do it. Perhaps the companion star evolved, changing the dynamics of the system. In a magnetar, a starquake could trigger a change. The crust of the neutron star can crack under the stress of the magnetic field, suddenly altering the field geometry and the emission properties. In an isolated pulsar, changes in the magnetosphere could alter the emission. Perhaps the star crossed some threshold, switching from one emission mode to another. Any of these could explain why ASKAP J1832-0911 seems to have turned on recently, or perhaps it has been pulsing for a long time, but at a much fainter level, and something caused it to brighten dramatically, making it detectable for the first time. This is speculation, but it is grounded in what we have seen in other objects. Stars change, systems evolve. Nothing in the universe is truly static. Let us think about the broader implications of this discovery. ASKAP J1832-0911 is more than just an interesting object. It is a challenge to our understanding. It sits at the boundary of what our models can explain. It pushes against the limits of our theories. And when that happens, we have two choices. We can stretch our existing theories to accommodate the new data, add new parameters, consider new scenarios, extend the models just far enough to include this object, or we can consider the possibility that our theories are missing something, that there is a gap, a phenomenon we have not accounted for. Both approaches are valid. Both have their place in science. Often the first approach works. We discover a new object that seems strange, but with some adjustments to the models, it fits. It becomes part of the known landscape. But sometimes the first approach fails. The object refuses to fit, no matter how we adjust the models. And that is when the second approach becomes necessary. That is when we begin to suspect we are seeing something truly new. It is too early to say which case ASKAP J1832-0911 represents. The data are still coming in. The models are still being refined, but the object has already forced astronomers to think more carefully about the boundaries of possibility. How slowly can a neutron star spin and still emit? We thought we knew. ASKAP J1832-0911 suggests we might be wrong. How strong can a white dwarf's magnetic field be? We thought there were limits. Perhaps those limits are higher than we assumed. Can intermediate mass black holes exist in the galaxy? We think they can, but we have very few confirmed examples. Perhaps ASKAP J1832-0911 is one. These are important questions, and they matter not just for this one object, but for our understanding of the universe as a whole, because if ASKAP J1832-0911 is not unique, if there are many such objects, then our models must account for them. And that might require rethinking some of our assumptions about how stars evolve, how they die, what they become. Let us consider the discovery process itself, how this object was found, and what that tells us about the future. ASKAP is a powerful telescope, but it is not the most sensitive radio telescope in the world. It is not designed to see the faintest signals. What makes ASKAP special is its field of view. It can observe many square degrees of sky at once, and it can process data quickly, searching for transients in real time. This is crucial for finding objects like ASKAP J1832-0911. Transients appear without warning. They can be anywhere in the sky. If your telescope has a narrow field of view, you will miss them. But if your telescope can watch large areas simultaneously, your chances improve dramatically. ASKAP is part of a new generation of radio telescopes designed for wide-field surveys. Meerkat in South Africa is another. The future square kilometre array will be even more powerful. These instruments are changing radio astronomy. They are turning it from a targeted science where you point at a known object and study it, into a discovery science where you survey the sky and see what you find. The same shift is happening in X-ray astronomy, though more slowly. X-ray telescopes are harder to build. Their field of view is typically small. Chandra, the telescope that detected the X-rays from ASKAP J1832-0911, has a very narrow field of view, just a fraction of a degree across. The fact that Chandra happened to be pointing at the same patch of sky as ASKAP at the same time was pure luck. But luck can be improved. New X-ray missions are being designed with wider fields of view. The Einstein probe launched recently is one example. It can survey larger areas, catching transients that Chandra would miss. The proposed Advanced X-ray Imaging satellite would be even better. Faster, more sensitive, able to respond quickly to alerts from radio telescopes. Imagine a future where radio telescopes like ASKAP detect a slow transient and immediately alert an X-ray telescope. Within hours, the X-ray telescope slews to the target and confirms whether it is emitting X-rays. This kind of coordinated, rapid response astronomy is becoming possible, and it will find many more objects like ASKAP J1832-0911, perhaps dozens, perhaps hundreds. And when we have a population of these objects, we can begin to study them statistically. We can look for patterns, correlations. We can see which properties vary and which stay constant. That is when real understanding begins to emerge. Right now, ASKAP J1832-0911 is a sample of one, and it is very hard to draw conclusions from a sample of one. But if we find 10 more, or 50 or 100, the picture will change. We will see which features are common and which are rare. We will be able to test models systematically. This is how astronomy progresses. A single discovery raises questions. More discoveries provide answers, and eventually a coherent picture emerges. We are still in the early phase with ASKAP J1832-0911, the phase of questions. But the tools to find answers are being built. The surveys are running. The telescopes are watching, and the universe is vast, full of objects we have not yet seen, full of phenomena we have not yet imagined. Somewhere out there, other objects are pulsing slowly. Other beams are sweeping through space. Other mysteries are waiting to be discovered. ASKAP J1832-0911 is just the beginning. The search for similar objects has already begun. Astronomers have started examining the other known long-period transients, the handful of objects discovered since 2022, each pulsing slowly, each radio bright, each mysterious in its own way. The question now is simple. Do any of them emit X-rays? Teams are requesting observing time on X-ray telescopes. Chandra, XMM Newton, Swift, NuSTAR. Every available instrument that can see high-energy light, they are pointing these telescopes at the positions of known LPTs. Watching, waiting, hoping to catch an X-ray pulse. If they find X-rays from other LPTs, it would tell us something profound. It would tell us that ASKAP J1832-0911 is not a fluke, not an oddball, but rather a representative of a whole class of objects. It would mean that perhaps all long-period transients are X-ray sources we simply had not looked before, and that would narrow the possibilities considerably. Because any model proposed to explain ASKAP J1832-0911 would have to explain all of them. But if the searches come up empty, if the other LPTs show no X-rays, that tells us something different. It tells us ASKAP J1832-0911 truly is special, different from its cousins, perhaps in a different evolutionary state, perhaps a different type of object altogether. Either result would be valuable. Either result would teach us something. For now, the searches continue, the data are being collected, and astronomers wait for the answers. While we wait, let us consider what it means to observe something at multiple wavelengths. Light is not one thing, it is a spectrum, a continuum of energies from low-frequency radio waves to high-energy gamma rays. Every wavelength tells us something different, reveals a different aspect of the object. Radio waves tell us about magnetic fields, about coherent emission processes, about non-thermal particles moving at high speeds. X-rays tell us about hot gas, about energetic particles, about the presence of strong gravity or intense radiation. Visible light tells us about stars, about temperatures in the thousands of degrees, about the surfaces of objects. Infrared light penetrates dust, reveals cool objects, shows us things hidden from optical telescopes. Each wavelength is a different window, and to truly understand an astronomical object, we need to look through as many windows as possible. This is called multi-wavelength astronomy, and it has become essential to modern astrophysics. ASKAP J1832-0911 is invisible at most wavelengths. In visible light, we see nothing. In infrared, nothing conclusive. In gamma rays, so far, nothing. But in radio and X-rays, it shines, pulses, reveals itself. This tells us immediately that the object is not like the sun. The sun is bright in visible light. ASKAP J1832-0911 is not. The object is not a normal star. It is something compact, something where extreme processes are at work. The radio emission tells us there is a strong magnetic field. The X-rays tell us there is high-energy activity. Together, they constrain the possibilities. This is why the chance alignment of ASKAP and Chandra was so crucial. Without both pieces of information, we would know much less. Imagine if only the radio emission had been detected. We would have another long-period transient. Interesting, but without the X-ray data, we would not know it was special. we would not know it was different from the others. The X-rays are what make ASKAP J1832-0911 extraordinary, and this is a lesson for the future. To understand rare transients, we need multi-wavelength coverage. We need radio telescopes and X-ray telescopes working together. Infrared, optical, gamma ray, all of them. The more wavelengths we observe, the more complete the picture becomes. Some observatories are already planning coordinated campaigns. When ASKAP or another radio telescope detects a new slow transient, alerts will be sent out immediately. X-ray telescopes will respond, optical telescopes will point, infrared instruments will observe. Within days, perhaps hours, we will have data across the spectrum, and we will know much more, much faster than we did for ASKAP J1832 or 0911. This kind of coordination is becoming easier. Networks of telescopes are being linked. Automated alert systems are being developed. The goal is to catch transients while they are still active, before they fade, before the opportunity is lost, because the universe does not wait for us. Transients appear and disappear on their own timescales. If we are not ready, we miss them. ASKAP J1832-0911 was caught partly by luck. The next one might be caught by design. Let us return to the theoretical models, to the possibilities we discussed earlier. Each model makes predictions, and those predictions can be tested. If ASKAP J1832-0911 is an ultra-slow magnetar, certain things should be true. The X-ray spectrum should show specific features, perhaps absorption lines from the neutron star's atmosphere, perhaps a thermal component from the star's surface. The radio emission should be coherent, highly polarized, with properties similar to pulsar emission, but slower. The pulse profile should be consistent with a rotating beam, perhaps a double-peaked structure, as we sometimes see in pulsars when both magnetic poles sweep past our line of sight. And there might be timing irregularities, glitches, sudden changes in the pulse period as the neutron star's crust cracks or its magnetic field rearranges. These are testable predictions. Observations can confirm or rule them out. If the object is a white dwarf binary, other things should be true. There should be a companion star, perhaps faint, perhaps hidden by dust, but detectable in infrared or optical light with sensitive enough instruments. The pulse period might not be perfectly stable. Orbital motion could cause small variations. Doppler shifts as the white dwarf moves toward and away from us. The X-rays might show evidence of accretion. A power law, spectrum, perhaps emission lines from hot gas spiraling onto the white dwarf. And the radio emission might have characteristics different from pulsars, perhaps broader pulses, perhaps different polarization properties. Again, these are testable. Given enough data, we can check. If the object is an intermediate mass black hole with a precessing jet, still other predictions follow. The pulse period should be extremely stable. Precession timescales are typically very steady. The X-ray and radio emissions should be consistent with a jet. A non-thermal spectrum, perhaps variability on short timescales within each pulse as turbulent structures pass through the jet. There should be no thermal component, no hot surface, no stellar atmosphere, because black holes do not have surfaces in the same way stars do. And if we could resolve the object spatially, we might see a jet structure. Though at 15,000 light-years, this would require extremely high resolution, beyond what current instruments can achieve. These predictions too can be tested, some immediately, some with future observations. The point is that science progresses by making predictions and testing them. Models are not just ideas. They are frameworks that generate testable consequences. And ASKAP J1832-0911 provides a test case, a laboratory, a way to see which models hold up under scrutiny. Over the coming years, as more data accumulate, some models will be ruled out, others will become more plausible, and eventually one will emerge as the best explanation. Or perhaps none will. Perhaps the data will refuse to fit any existing model, and that will tell us we need to think differently. Let us consider the pulse itself in more detail. The 2-minute burst of energy. 2 minutes is a long time in astrophysical terms. For a pulsar, a pulse lasts milliseconds. For a flare star, a flare might last minutes to hours, but without such regularity. What happens during those 2 minutes? Does the emission rise smoothly, peak and fall smoothly? Or are there fluctuations? Substructure? The light curves from ASKAP and Chandra show a relatively smooth pulse, a rise, a peak, a decline. But the time resolution is limited. There could be faster variations hidden within the data. Future observations with better time resolution will reveal more. Perhaps there are rapid flickers within each pulse. Perhaps the emission is not smooth but structured. If there are rapid variations, that would tell us about the size of the emitting region, because nothing can vary faster than the light travel time across the source. If we see variability on timescales of, say, 1 second, that tells us the emitting region cannot be much larger than 300,000 kilometers. The distance light travels in 1 second. For a neutron star, 20 kilometers across, this is not a strong constraint. The emitting region could be the entire magnetosphere, which extends thousands of kilometers. For a white dwarf, thousands of kilometers across, similar reasoning applies. For a black hole, the size depends on the mass. An intermediate mass black hole of 1,000 solar masses would have an event horizon a few million kilometers across, still consistent with second-scale variability. So time resolution matters. It provides constraints, and those constraints help us distinguish between models. Another detail worth considering is the spectrum, the distribution of energy across different frequencies. In radio, ASKAP observes at a specific frequency band, around 1 GHz, but the source might emit at other frequencies too, higher or lower. Follow-up observations with other radio telescopes have measured the spectrum, the brightness at different radio frequencies, and the spectrum appears relatively flat. The source is bright across a wide range of frequencies. This is somewhat unusual for pulsars, which often have steep spectra. A flat spectrum suggests the emission mechanism is efficient across a broad range. This is more consistent with a coherent process, or with emission from a jet. It is less consistent with thermal emission, which typically has a characteristic shape determined by the temperature. In X-rays, the spectrum is harder to measure. The signal is fainter. But early measurements suggest a non-thermal spectrum, a power law, consistent with synchrotron emission or inverse Compton scattering, not consistent with a hot black body. Not the spectrum you would expect from the surface of a star. This is another piece of the puzzle, another constraint. Let us think about the future of this field, about where this discovery might lead. If ASKAP J1832-0911 is part of a larger population, and if we can find many more examples, we will begin to see patterns. Perhaps some will be brighter, some fainter, some will pulse faster, some slower. We might find correlations between pulse period and luminosity, between X-ray brightness and radio brightness, between long-term variability, and pulse stability. These correlations would be clues. They would point toward underlying physical relationships. They would help us build a coherent theory. This is how astronomy often works. A single object is a puzzle. 10 objects are a sample. 100 objects are a population, and populations reveal trends. Pulsars, for example, were mysterious when the first few were discovered. But as hundreds, then thousands were found, patterns emerged. Relationships between period and period derivative, between age and magnetic field strength. These relationships are now codified in pulsar theory. They tell us how pulsars evolve, how they spin down, how they age. If long-period transients follow a similar path, we will eventually have a theory of LPTs, a framework for understanding them, predictions about how many exist, where they come from, what they become. But we are not there yet. We are still in the early exploratory phase, the phase of discovery and characterization, and ASKAP J1832-0911 is leading the way. There is something deeply satisfying about this kind of work, about observing something we do not understand, measuring it carefully, thinking about it deeply, not rushing to conclusions, not forcing the data to fit preconceptions, but letting the universe speak for itself. This is the essence of astronomy, of science in general. We do not invent the answers, we discover them by looking, by measuring, by thinking. And sometimes the universe shows us something unexpected, something that does not fit, something that challenges us. That is when the work becomes most interesting, when the mystery is deepest, when the path forward is unclear, because it is in those moments that we have the opportunity to learn something truly new. ASKAP J1832-0911 is one of those moments. Let us consider the human side of this discovery, the people involved, the process of scientific collaboration. Astronomy is not a solitary pursuit. It involves teams, collaborations, institutions spread across the globe. The discovery of ASKAP J1832-0911 required many people: telescope operators, data analysts, software engineers, theorists, observers. Someone had to build ASKAP. Someone had to write the software that processes its data in real time. Someone had to notice the signal among all the noise. Someone had to think to check the Chandra archives. Someone had to analyze those X-ray data. Someone had to recognize the match. And then someone had to coordinate the follow-up, to write the proposals, to request telescope time, to bring together the expertise needed to understand what had been found. Science is a collective endeavor, a conversation across continents and disciplines, and it takes time. The discovery was made in late 2023. The paper was published in early 2025. More than a year of analysis, checking, verifying, writing, reviewing. This is normal. This is how science works. Carefully, methodically, with attention to detail. Because extraordinary claims require extraordinary evidence. And a claim that a new type of object has been discovered is extraordinary. The team had to be sure. They had to rule out other explanations, instrumental artifacts, interference, misidentifications. Only when they were confident did they publish, and even then the paper is not a final answer. It is a report of observations, an invitation for others to investigate further. Science progresses through this process: observation, publication, discussion, more observation, refinement of ideas. It can be slow, but it is reliable. It is how we build knowledge that lasts. And now, teams around the world are responding, proposing new observations, developing new models, writing papers, holding conferences. ASKAP J1832-0911 has become a focal point, a problem that the community is collectively working to solve. This is how breakthroughs happen, not in isolation, but through the combined efforts of many minds, many perspectives, many approaches. Let us return once more to the object itself, to that point of light in scutum, pulsing quietly, regularly, every 44 minutes. It has been pulsing for a long time, probably for thousands of years, perhaps much longer, long before humans knew it was there, long before we had radio telescopes, long before we understood what radio waves were. It pulsed through the nights when our ancestors looked up at the stars and wondered. It pulsed through the centuries of darkness, through the birth of astronomy, through the invention of the telescope. It pulsed through the 20th century as we began to explore the radio sky, through the discovery of pulsars, through the space age, and it will continue to pulse long after we have solved its mystery, long after we understand what it is, long into the future. This is humbling, in a way. The universe does not perform for us. It simply exists, and we are fortunate to be able to observe it, to learn from it. ASKAP J1832-0911 does not know we are watching. It does not care. It continues its cycle, indifferent to our curiosity, and yet, through our instruments and our intellects, we reach out across 15,000 light years. We detect its pulses, we measure its properties, we think about its nature, we connect with it in a sense, across the vast emptiness of space, across the gulf of time. This is what astronomy allows us to do, to touch the unreachable, to know the unknowable, to bring distant objects into our understanding. 15,000 light years is an almost incomprehensible distance. Light, travelling at 300,000 kilometers per second, takes 15,000 years to cross it. The light we see from ASKAP J1832-0911 today left that object 15,000 years ago, when human civilization was just beginning, when the Ice Age was ending, when our species was spreading across the continents. The pulses we detect today are ancient messages, sent long ago, arriving only now, and yet they tell us about the present state of the object, because for all practical purposes, that object is not changing on human timescales. What it was 15,000 years ago is what it is now. This is the strange nature of astronomical observation. We see the past, but we interpret it as the present, and in doing so, we learn about the universe, about how matter and energy behave under extreme conditions, about the life cycles of stars, about the laws of physics. ASKAP J1832-0911 is a laboratory, a natural experiment, a place where conditions exist that we cannot reproduce on Earth, magnetic fields billions of times stronger than anything we can create, densities beyond our imagination, energies that dwarf our most powerful accelerators. By studying such objects, we test our theories in regimes far beyond what is accessible in the laboratory. And sometimes we find that our theories work. They predict correctly. They explain what we see. And sometimes we find that they do not. That something is missing. That we need to think more deeply. ASKAP J1832-0911 is one of those cases. Our theories struggle. And that tells us something important. It tells us we have more to learn. There is a certain beauty in this, in not knowing, in standing at the edge of understanding, looking out into the unknown. It is uncomfortable, perhaps, unsettling. We like to have answers, to understand, to know. But the unknown is where discovery happens, where new knowledge is forged, where science advances, and ASKAP J1832-0911 invites us into that space of not knowing, of questioning, of wondering. It asks us to be patient, to observe carefully, to think clearly, to remain open to possibilities, because the answer, when it comes, might surprise us. It might not be what we expected. It might require us to change how we think about stellar remnants, about magnetic fields, about the cycles of matter and energy in the universe. Or it might fit neatly into what we already know with just a small adjustment, a parameter we had not considered, a process we had overlooked. Either way, we will learn. We will know more than we do now. And that is the goal. Not to confirm what we believe, but to discover what is true. The 44-minute pulse continues, regular, steady, unchanging, at least on the timescales we have observed so far. Each cycle, another 2 minutes of radio and X-ray light, another brief illumination, another beacon across the darkness, and we watch, we measure, we wonder. What is this object? What makes it pulse? Why this period? Why these wavelengths? The questions remain. But with each observation, we come closer to answers. With each measurement, we narrow the possibilities. With each theoretical paper, we refine our thinking. Slowly, patiently, the picture emerges. Not all at once, not in a sudden flash of insight, but gradually, piece by piece. This is the nature of scientific progress. Not a straight line, not a simple path, but a winding journey with detours and dead ends, with surprises and setbacks, and sometimes with moments of clarity, when the data align, when a model clicks, when understanding dawns. We are not there yet with ASKAP J1832-0911, but we are on the path, and the journey itself is worthwhile. Because in seeking to understand this one object, we learn about many things. We learn about radio telescopes and X-ray satellites, about data analysis and signal processing, about the challenges of detecting faint signals in noisy data. We learn about neutron stars and white dwarfs and black holes, about magnetic fields and accretion disks and jets, about the physics of extreme environments. We learn about collaboration and communication, about how scientists work together across borders and disciplines, and we learn about the universe itself, about its diversity, its complexity, its capacity to surprise us, all from one object, one pulsing point of light, 15,000 light years away. This is the power of astronomy, to take a single observation and extract from it layers of meaning, layers of insight. And ASKAP J1832-0911 has given us much to think about, much to explore, much to discover. The work continues, the observations continue, the thinking continues. And somewhere in scutum, indifferent to our efforts, the object pulses on. Every 44 minutes, like clockwork, like a heartbeat, like a cosmic metronome marking time in the darkness, waiting for us to understand. We have journeyed through the mystery of ASKAP J1832-0911, through its discovery, its properties, its puzzling nature. We've considered the models, the possibilities, the challenges, but there is more to explore, more layers to this story, because this object exists within a context, within a galaxy, within a universe that has evolved over billions of years, and understanding that context helps us understand the object itself. Let us step back. Let us consider where ASKAP J1832-0911 came from, what its history might have been. If it is a neutron star, it was born in a supernova, the explosive death of a massive star. Somewhere in the Milky Way, millions of years ago, perhaps tens of millions, a star many times the mass of the Sun reached the end of its life. It had burned through its fuel, hydrogen first fusing into helium, then helium into carbon and oxygen, then heavier elements, silicon, iron. But iron cannot fuse and release energy. Iron is the end of the line. When a star's core turns to iron, fusion stops. And without fusion to support it, the core collapses. In less than a second, it falls inward, compressing to nuclear densities. The collapse rebounds. A shock wave forms. The outer layers are blown away in a brilliant explosion, a supernova. And at the center, a neutron star is born, 20 kilometers across, dense beyond imagining, spinning rapidly, magnetized powerfully. This is the standard picture. And if ASKAP J1832-0911 is a neutron star, this is where it came from. But then something happened. Something changed it, slowed it down, made it different from ordinary pulsars. Perhaps it is very old, billions of years old, spun down by magnetic braking over eons until its rotation period stretched from milliseconds to minutes. But this seems unlikely. Most neutron stars stop emitting long before they spin this slowly. They cross the death line. They fade into silence. Unless there is something special about this one, some unusual property of its magnetic field, some configuration that allows it to keep emitting even at such a slow spin. Or perhaps it is not that old, perhaps something else slowed it down. Interaction with a companion star, accretion of matter, some event that altered its spin. These are speculations, educated guesses based on what we know about neutron stars, but they are not confirmed. If it is a white dwarf, its history is different. White dwarfs are not born in explosions. They are born in gentleness, in the slow fading of a star like the Sun. When a Sun-like star exhausts its fuel, it swells into a red giant. The outer layers drift away, forming a planetary nebula. And the core, no longer producing energy, cools and contracts. What remains is a white dwarf, supported not by fusion or gas pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further. White dwarfs are stable. They cool slowly over billions of years. They do not pulse like neutron stars. They do not have the same kind of magnetic activity, unless they are in a binary, unless they have a companion star providing matter, providing energy. Then they can become active, they can flare, they can emit across many wavelengths. If ASKAP J1832-0911 is a white dwarf binary, it has lived a complex life, formation, cooling, capture of a companion, or survival of a companion through the red giant phase, evolution of the binary, changes in the orbit, accretion, a long intricate history, spanning billions of years. And somewhere along that path, it became the object we see today, pulsing every 44 minutes, emitting radio and X-rays. If it is a black hole, the history is different again. Intermediate mass black holes are enigmatic. We do not know how they form. There are theories, but no consensus. Perhaps they form from the direct collapse of very massive stars. Stars hundreds of times the mass of the Sun, which collapse without exploding. Perhaps they form from the merger of smaller black holes, two stellar black holes spiraling together, colliding, forming a larger one. Perhaps they are the seeds of supermassive black holes, objects that formed in the early universe and grew over time. Or perhaps they form in dense star clusters, where many stars crowd together, collide, merge, creating ever larger objects until a black hole forms. Any of these paths could lead to an intermediate mass black hole. And if ASKAP J1832-0911 is 1, It has followed one of these paths. It has existed for a long time, perhaps since the early days of the galaxy, perhaps since shortly after the Big Bang. It has wandered through space, perhaps ejected from a star cluster, perhaps drifting in the galactic disk, and at some point it captured matter, perhaps from a companion star, perhaps from the interstellar medium. That matter formed an accretion disk, and the disk began to glow, to emit radiation, to launch jets. And now, as the disk precesses, we see the pulses, the signature of a black hole feeding quietly in the depths of the galaxy. This is all speculation. We do not know which history is correct. We do not know which path ASKAP J1832-0911 has travelled. But thinking about its history helps us frame the right questions, helps us understand what we are looking at. Because objects do not appear fully formed. They have origins, they evolve, they change over time, and understanding that evolution is part of understanding the object itself. Let us consider the environment, the region of space where ASKAP J1832-0911 resides. It is in the galactic disk, the flat star-filled plain of the Milky Way. This is a crowded region, rich in gas and dust, rich in stars of all ages, rich in stellar remnants, but it is also a dynamic region. Stars orbit the galactic center, gas clouds collide and form new stars, supernovae explode, enriching the medium with heavy elements. ASKAP J1832-0911 is part of this ecosystem. It moves through space, following its orbit around the galaxy. At 15,000 light-years from Earth and located in Scutum, it is likely in the inner regions of the galaxy, closer to the galactic center than we are. The Sun orbits at about 26,000 light-years from the center. If ASKAP J1832-0911 is 15,000 light-years from us and in roughly the same direction as the galactic center, it is probably orbiting at a smaller radius. Closer to the center, conditions are different. The stellar density is higher. Encounters between stars are more common. The gravitational field is stronger. These factors might be relevant. If ASKAP J1832-0911 is in a binary, its companion might have been captured during a close encounter, or the binary might have been disrupted by such an encounter. The environment shapes the history, and the history shapes the present. This is the web of connections that astronomers work to unravel. Not just what an object is, but where it is, how it came to be, what influenced it. Let us think about the future, not just the future of our observations, but the future of ASKAP J1832-0911 itself. What will happen to it? How will it change? If it is a neutron star, it will continue to spin down. Gradually, over millions of years, its rotation will slow further. Perhaps the pulses will weaken. Perhaps they will stop altogether as the star crosses some threshold and the emission mechanism shuts off. Or perhaps the star will continue to pulse, slower and slower, for billions of years. Eventually, the neutron star will cool. Its surface temperature will drop. It will fade in X-rays. It will become dark, cold, invisible. A dead remnant, drifting through space. Silent. If it is a white dwarf binary, its future depends on the companion, on the mass transfer, on the orbital evolution. Perhaps the accretion will continue. Perhaps the white dwarf will accumulate more and more matter until it reaches a critical mass. At that point, fusion might ignite. The white dwarf might explode in a Type Ia supernova, one of the brightest explosions in the universe. Or perhaps the mass transfer will slow. The system will quiet. The pulses will fade. The white dwarf will cool and darken. Or perhaps the orbit will change. The stars will spiral closer or drift apart. the dynamics will shift. The emission will change. If it is a black hole, its future is more certain. Black holes are patient. They exist for timescales that dwarf the age of stars. The accretion disk will eventually dissipate. The matter will run out. The jets will fade. The pulses will stop. And the black hole will continue to exist, invisible, dark, waiting. Perhaps in billions of years, it will encounter another star, capture it, begin accreting again, flare back to life. Or perhaps it will wander silently through the galaxy for the rest of time, an invisible presence, a gravitational field, nothing more. These futures are distant, on timescales we cannot observe, on timescales that make human history seem like the blink of an eye, but they are part of the story, part of the cycle of matter and energy in the universe. And ASKAP J1832-0911 is one moment in that cycle, one brief flicker, one pulse in the cosmic story. Let us return to the present, to what we can observe, to what we can measure. There are still many observations to be made, many questions to be answered. What is the detailed shape of the pulse? Does it have substructure? Does it vary from cycle to cycle? What is the exact spectrum? How does the brightness change with frequency in both radio and X-rays? What is the polarization behavior? Does the polarization angle sweep across the pulse as it does in pulsars? Is the pulse period perfectly stable, or does it drift? Does it show glitches or timing noise? Are there emissions at other wavelengths we have not yet detected? Gamma rays, optical light, infrared? Is there a companion star? Can we detect it with sensitive enough instruments? Each of these questions requires observations, careful, patient observations, with the best instruments we have. And each answer will refine our understanding, will rule out some models, will support others. This is the work ahead, the work that astronomers are now undertaking, and it will take time, years probably, perhaps decades, because good science is not rushed, it is thorough, it is careful, it is built on solid foundations of data and analysis, but the wait will be worth it, because when the answer comes, it will be robust, it will be reliable, it will be knowledge we can build on, and that knowledge will extend beyond ASKAP J1832-0911 itself. It will inform our understanding of stellar remnants in general, of magnetic fields, of accretion, of the life cycles of stars. This is how science progresses, one discovery at a time, one object at a time, building a framework of understanding that encompasses more and more of the universe. Let us consider the broader significance of this discovery, what it means for astronomy as a field. ASKAP J1832-0911 is a reminder that the universe still holds surprises, that we have not catalogued everything, that there are phenomena we have not yet seen. This is important because it keeps us humble. It reminds us that our models are approximations, that our theories are works in progress, and it keeps us curious. It drives us to keep looking, to keep exploring, to keep questioning. This is the spirit of science, not to assume we know everything, but to always be open to the possibility that we might be wrong, that there might be more to discover. ASKAP J1832-0911 embodies that spirit. It challenges us. It invites us to think more deeply, to look more carefully, to consider possibilities we had not imagined. And in rising to that challenge, we grow as scientists, as a field, as a species. There is something profound about this, about humans, fragile and small, reaching out to understand the cosmos. We are made of the same atoms as the stars. Carbon, nitrogen, oxygen forged in stellar cores, scattered by supernovae. We are the universe trying to understand itself, consciousness emerging from matter, curiosity arising from chemistry. And when we study an object like ASKAP J1832-0911, we are engaging in a deep act of connection, connecting with the cosmos, with the processes that shaped it, with the forces that govern it. This is what makes astronomy more than just a science. It is a philosophical endeavour, a search for meaning, a quest to understand our place in the vastness of space and time. ASKAP J1832-0911 is 15,000 light-years away, but in another sense, it is not distant at all. It is part of the same universe we inhabit, subject to the same laws, made of the same substance, and by studying it, we learn about ourselves, about where we came from, about the processes that made our existence possible. Because every atom in our bodies was once inside a star. Every breath we take contains oxygen forged in a stellar core. Every thought we think is powered by energy from atoms that were once part of the cosmos. We are not separate from the universe, we are part of it, and astronomy is how we explore that connection. ASKAP J1832-0911 is a teacher. It teaches us about physics, about magnetism and gravity and radiation, but it also teaches us about patience, about the value of careful observation, about the importance of not jumping to conclusions. It teaches us about collaboration, about how many minds working together can achieve more than any one person alone. It teaches us about humility, about accepting that there are things we do not know, and being comfortable with that uncertainty. These are lessons worth learning, not just for scientists, but for everyone. Let us think about the technology that made this discovery possible. ASKAP is a marvel of engineering, 36 dish antennas, each 12 meters across, spread across 6 kilometers of desert. They work together, combining their signals, forming a single powerful instrument with a huge field of view. The data rate is enormous, millions of measurements per second, processed in real time by sophisticated computers. This technology did not exist a generation ago. It is the fruit of decades of development, of incremental improvements in electronics, in software, in engineering, and it is part of a larger trend. Telescopes are getting better, more sensitive, faster, able to cover more sky. This is transforming astronomy from a science of targeted observations to a science of surveys and discovery. We are no longer just looking at objects we know about. We are searching the entire sky continuously for things we have never seen. This is how ASKAP J1832-0911 was found, not by pointing at a known object, but by surveying the sky and finding something new. And this approach will find many more surprises, objects we cannot yet imagine, phenomena we have not yet conceived of. The future of astronomy is one of discovery, of exploration, of encountering the unexpected, and the technology to make this possible is being built now. ASKAP is just the beginning. The square kilometre array will be even more powerful. New X-ray telescopes are being designed. New optical surveys are coming online. New infrared missions are being planned. All of them will contribute. All of them will find new objects, new mysteries, and each mystery will be an opportunity to learn, to grow, to expand our understanding. This is an exciting time to be an astronomer, to be alive in an era of discovery, to witness the universe revealing its secrets. ASKAP J1832-0911 is part of this larger story, a chapter in the ongoing exploration of the cosmos. But it is also a story in itself, complete, self-contained, a single object, a single mystery, and mysteries have a certain beauty, a certain appeal. They draw us in, they engage our minds, they challenge us, and in seeking to solve them we find meaning, purpose, connection, the 44-minute pulse, the radio waves, the X-rays, the unanswered questions. All of these are invitations to think, to wonder, to imagine. What is this object? What makes it pulse? What is its nature? We do not yet know, but we are working on it, patiently, carefully, thoughtfully, and one day we will know. The mystery will be solved, the answer will be clear, but until then we have the journey, the process of discovery, the experience of not knowing but seeking to know, and that in its own way is valuable, perhaps even more valuable than the answer itself, because the journey is where we grow, where we learn, where we become more than we were. ASKAP J1832-0911 is still out there, still pulsing, still mysterious, every 44 minutes, like clockwork, a beacon in the darkness, a question mark in the cosmos. It does not know we are watching, it does not care, it simply is. And we, from our small planet, from our brief moment in cosmic time, reach out to understand it with our telescopes, with our mathematics, with our curiosity. We reach across 15,000 light years, across the gulf of space, across the barriers of ignorance, and slowly, carefully, we begin to understand. Not all at once, not completely, but piece by piece, step by step. This is the work of science. This is the work of humanity. To look up at the stars and ask why. To seek answers. To never stop wondering. And ASKAP J1832-0911, with its steady pulse, with its mysterious nature, reminds us why this work matters. Because the universe is vast, and we are small. But our capacity to understand is not small. Our ability to observe, to measure, to think, to learn. That is vast. That is powerful. That is what makes us human. And in studying this one object, this one pulsing point of light, we are exercising that capacity. We are being fully human, curious, thoughtful, patient, determined, reaching for understanding, reaching for knowledge, reaching for connection with the cosmos that made us. This is the story of ASKAP J1832-0911, not just a story of an astronomical object, but a story of human curiosity, human persistence, human wonder, a story that is still being written, still unfolding, still revealing itself. And we are privileged to witness it, to be part of it, to contribute to it. In our small way, from our small planet, we are part of the cosmic story, part of the universe's effort to understand itself. And that is something profound, something beautiful, something worth celebrating. The pulse continues. 44 minutes, then another pulse, then another, steady, regular, unchanging, a cosmic metronome, marking time in the vastness of space, waiting patiently for us to understand, inviting us deeper into the mystery, calling us forward into the unknown, and we answer that call with our telescopes, with our minds, with our wonder. We observe, we measure, we think, we learn, and slowly the mystery begins to yield. The fog begins to lift. The picture begins to emerge. Not yet, not today, but someday. And when that day comes, when we finally understand what ASKAP J1832-0911 is, we will look back on this time with fondness, the time of not knowing, the time of wondering, the time of exploration, because that is when the journey was most alive, most vibrant, most full of possibility. The answer, when it comes, will be satisfying. It will be knowledge gained, understanding achieved. But this moment, this present moment of mystery, has its own value. its own beauty. The beauty of the unknown, the beauty of the question, the beauty of the search. And ASKAP J1832-0911 gives us that gift. The gift of mystery, the gift of wonder, the gift of curiosity. For that we can be grateful. Grateful to the universe for its complexity, its diversity, its capacity to surprise us. Grateful to the astronomers who found it, who study it, who work to understand it. Grateful for the technology that makes observation possible, for the mathematics that makes analysis possible, for the community that makes progress possible. And grateful for the mystery itself, for the reminder that there is always more to learn, always more to discover, always more to wonder about. ASKAP J1832-0911 pulses on in the constellation Scutum, 15,000 light years away, hidden in the depths of the Milky Way. Every 44 minutes, radio waves, X-rays, together, in perfect synchronization. A cosmic puzzle, a challenge, an invitation, and we, the watchers, the measurers, the thinkers, continue our work. Patient, persistent, hopeful, knowing that understanding will come, in time, with effort, with thought. And until then, we have the journey, the wonder, the mystery, and that perhaps is enough. The pulse continues, the search continues, the universe waits, and we reach out across the darkness, seeking light, seeking understanding, seeking connection, one pulse at a time, one observation at a time, one thought at a time, slowly moving forward, into the unknown, into the mystery, where discovery awaits, where knowledge grows, where wonder lives. This is ASKAP J1832-0911. This is astronomy. This is the human journey, and it continues.